So before we get started, if everyone could go to that link that's on the board, it's a GitHub repository. And for those joining us remotely, it is github.com/jepsonnomad/raster intro. Once again, that's github.com/jepsonnomad/raster intro. And you should be able to clone and download the repository as you please. There's 3 R scripts on there and 1 PDF of the PowerPoint that I'm going to share. And so without further ado, I will begin with a brief presentation on rasters. Can I make that? Oh, it goes away on its own. Cool. Okay, so I'm Christian. I'm a PhD student in the ecology graduate group. And I do a lot of work with satellite data and remote sensing, and because of that, I end up using this particular format of data called rasters. So to give you just a brief background on rasters, a raster is just a grid of values. And so technically a matrix could be interpreted as a raster. Really what we're interested in is some number of columns in our grid, some number of rows in our grid, and each cell in that grid has a value. And what that can translate into are lots of different types of data. So here on the left, we're looking at the elevation in Yosemite National Park. And really high values mean high elevation, low values mean low elevation. On the top right, that's a national land cover data set. So that's more of a categorical type of raster where a certain value might indicate a shrub-dominated landscape, a different value might indicate like an evergreen forest, et cetera, et cetera. And then finally, a picture that we take with our phone is a raster. It's a grid of values. It has 3 layers rather than 1, and each layer represents red, green, and blue for that area of the picture. We can combine red, green, and blue to create these visually stimulating images like that picture of Ulcia in the High Sierra. Raster data is one type of geospatial data. People also commonly use vector data, which are points, lines, and polygons. So we could have the polygon that outlines Yosemite National Park. We could have the line of Tioga Road, and we could have the point of the Wakewell campsite. So these are types of vector data that we will ultimately use today in order to facilitate our use of raster data. The last really important thing that I need to introduce here before we actually dive into some code are coordinate reference systems. The Earth is round and 3-dimensional, but we use these types of data in a 2-dimensional format. So there's this mathematical flattening that has to happen in order to be able to take some parcel of Earth and put it on our computer screen. And there's lots of ways to do this, and no way is perfect. Every type of flattening of Earth involves some distortion. So we can wrap a cylinder around Earth and kind of image it from every part of the cylinder and then flatten that out. We could wrap a cone around the Earth and image it from every part of the cone and flatten that out. And there's several ways to do it. And ultimately, that figure doesn't do a very good job of showing what types of distortion we create. This figure does. So in one form of flattening the Earth, we could end up with a really large Greenland in the Arctic and a really tiny Africa. But in reality, I think Greenland is what, like a 1/7 the size of Africa? So if we used instead like the Peters projection, I think this is Peters projection, we have a very tiny Greenland in the Arctic and a much more representative size of Africa. And then there's several other ways. I mean, there's like a ton of ways to do this. These are just 6 examples of different types of flattening and trying to illustrate that each type of flattening might best represent the area of space you're working in. So there's a few properties of a raster data set that we need to introduce before we actually play with rasters. The first is dimensions. Every raster data set has dimensions, whether it's a picture that you took with your camera or some piece of satellite imagery that you downloaded. And that's just the number of rows and the number of columns that we have in the data set. But if we're working with geospatial raster data sets, there's a few other components that we need to think about. First is extent. So extent is similar to dimensions, but Not really exactly. Extent is basically the spatial bounding box of the area we're working in. So you have an X minimum and an X maximum and a Y minimum and a Y maximum representing the endpoints of where this data of interest exists in Earth. So that could be represented in latitude and longitude, or in UTM coordinates, which is another type of projection system, or any number of other types of units that correspond to the projection system we're working in. We also have resolution because we need to know how big a given pixel in the raster data set is. So when I take a picture with my phone of Connor's face, a pixel might be 1 millimeter by 1 millimeter because my phone has a really high definition camera. But a satellite is so far away from space that a pixel in a satellite image might be 30 meters or 250 meters on the side. And these are important things to think about when we're working with raster data, but it's also important in the actual construction of the raster data set itself. And the nice thing about these 3 components is that you can calculate the 3rd component if you have 2 of them. So if you know the extent and the dimensions of your data set, you can calculate the resolution basically by dividing the extent and the dimensions. I don't know how else to explain it. I feel like that makes sense. Does that make sense? Okay.
What was the difference between extent and dimensions?
So dimensions is just the number of cells from left to right and from top to bottom. And extent is the actual geographical bounding box of those cells. So I could draw a grid that covers all of the US, and if it has 10 cells wide, those grid cells are hundreds of kilometers wide. But if I draw a grid over the US that has 1,000 cells, then those cells are much tinier. Does that make sense? Okay. And then the final thing, the final property of a raster data set, if we're working with geospatial data, is this reference system. And here's another example of the types of, what's the word? Distortion that we can get from different types of projection systems. So the main goals today are to learn how to import a raster into R, identify these different raster components that we just talked about, perform some basic raster operations, and then visualize some of these data. And we're going to be using some data from WorldClimb, which Robert Hyman's in the Ecology and Evolution, Geography, something like that. He helped develop that, and then as well as California's Open Data Portal to get a California shapefile, which we'll need to work with. There's also some resources on the last slide here, lots of links to like ArcGIS websites and stuff. I kind of just threw them in while I was making the presentation, but they should be clickable in the PDF that you downloaded from GitHub. And then also some contact information for me if anybody has any questions. So without further ado, let's transition to I'm using RStudio. I'm assuming everybody is everybody using RStudio? Is anybody not using RStudio? Okay, that's great. So the first script that we're going to work with is this script 000 intro to rasters. And we're going to need to download one file before we begin. So on line 27, you'll see there's a link to California data repository. If you could just follow that link and download the file, yeah.
Can you zoom in just a little on your
Is that like Command plus?
Yep.
Nice.
That's perfect. Thank you.
Oh, that was good?
Yeah.
Okay. Yeah, so if everybody could download that link, and there's no red stickies, so just give me a quick hand if you've gotten it downloaded, and we can move on once it's in everybody's hands. Gotcha. Does everybody have the link yet? I don't think I saw it. If you haven't downloaded it, raise your hand. Oh, cool. Okay. All right. So to begin with, we're going to have to, if you don't already have raster and RGDAL installed on your computer, or in R, you'll need to install those packages with the code on line 15. Those are super common geospatial libraries that we use to work with raster and vector data, respectively. If you already have them, then you can comment out that code and not run it, but we will need to install, load those two packages. And then if you want to set a working directory for wherever all this code that you downloaded lives, you can edit line 20 accordingly. But to begin with, let's acquire some data. So at this point, you should have downloaded the vector data set from line 27. It probably lives in your downloads folder unless you put it somewhere else. And we can use this line of code on line 29, read OGR, that comes from the RGBal library. It basically allows you to load a vector data set from a file. And the way it works is there's two arguments. The first one is this DSN, which is the directory that data set lives in. For me, it was in my downloads folder, and then under a subdirectory called ca-state-boundary. And then the layer, you're just including the layer name. You don't want an extension, so it should just be ca_state_tiger 2016, which is the big census thing that happened. I don't totally understand it, but it's a good boundary to use. So we can load that data set using line 29. And then it's always best when you're working with geospatial data to first actually look at the data rather than just assume that it is good. So there's a few ways to visualize what you're working with. I like to use this structure command because it lets you look at how everything exists in its object class in R. So over here on the console panel, we can scroll up and see that this California state shapefile is a spatial polygons data frame, which we'll end up needing to remember. And it has one observation, which is the outline of California. And what we're really interested in is further down, it will say what projection system we're using. Here it is at the very bottom. So can I move this? Nice. Yes, so we can see that these proj args, those are the arguments for the projection information, are, we're working with a Mercator projection, which was that one that had a really big Greenland, if you remember from a couple minutes ago, and then some other parameters that help the geospatial systems understand where everything is and how it is oriented on Earth. So beyond just looking at these weird text outputs from R, we can also use the base plotting functions to look at geospatial data. And if you plot California, you'll see a tiny California appear in your plotting window. And that looks like the shape of California, so I'm satisfied with that. Next, we're going to access some actual raster data. And thankfully in this raster package, there is a function called getData because Robert Hymans also wrote this package. So he made the package able to access the data from the data set that he put online. And that is this getData function. And it requires a few arguments. We're interested in the world climate data, which is a baseline historical climate data set. And we're going to access the maximum temperature element of that data set, which will be a 12-band raster that has global maximum temperatures for each month of the year, organized by layer. And you specify a resolution argument. I would recommend keeping this at 10, which is the coarsest resolution that you can use. If you used like 2.5, you get really tiny raster cells and a much bigger data set that would take forever to download and work with. So we'll use this coarse resolution max temp historical data set. And for you, it should have to download. Once you've used this, the software understands a caching system. So once you download a data set, it will store it in your computer. And if you try to run that same command again, it will, rather than try to download the data, it will access those data through your computer. And once we've downloaded it, we can look at that as well, running just the max temp historical. And we can see that it's a raster stack. It has dimensions of 900 by 2160, which are our number of rows and number of columns. It contains, how does that break down? 1.9 million cells, and there are 12 layers in it. And again, each of those layers corresponds with each of the months of the year. So as I mentioned in that full presentation, raster objects all have a series of components that are important for expressing how they exist in space. So there are the dimensions, which we use whenever. There is resolution, telling us how big the pixels are. And you'll note that these pixels are 0.16666, etc., by 0.16666, whatever. But they're 0.16 watts. Are they meters, miles, are they Earths? We don't know. So we'll get back to that. But remember that there's this sort of ambiguous resolution argument that we're going to need to think a little bit more about. There's also an extent argument. And this extent runs from negative 180 in the x-axis to 180 on the x-axis, and from negative 60 to positive 90 on the y-axis. And again, there's not units with this, so we need to think about what's going on here. The best way to think about that is to look at our reference system. So the CRS function on line 59 allows us to figure out what reference system this raster data set is using. And here we're looking at long lat CRS, which is units of longitude and latitude. So when we saw that that extent was negative 180 to positive 180 in the x dimension, we're talking about negative 180 degrees, which is 180 degrees west, to positive 180 degrees, which is 180 degrees east, which is the whole Earth in the x dimension.
Can you pause for a second? You just told us how we would know what the projection is, but I missed where you said how we do that.
Oh, so when you run CRS of max temp historical on line 59, that returns this CRS arguments output. And the first argument in that, the proj argument, is long lat. And anytime you're working with long lat, you're talking about degrees. If you were working in UTM, which we will end up coming to at some point, I think, then that would be in meters. I don't know the best way to keep track of all of the different reference systems you might use. And I think the internet would probably be a better resource than me for that part. But for now, we're working in long lat, which is all in degrees. And so we saw that our extent spanned the total longitudinal scope of the Earth. But in the y dimension, we're only going down to 60 degrees south, but we are going the whole way up to 90 degrees north. So we've lost Antarctica in this data set. And then finally, the last thing that I want to return to is this resolution function that lets us look at what the resolution of the data set is. 0.166 is a number, but without units. Now that we know that we're talking about longitude and latitude, we know we're talking about degrees. And 0.166 degrees is the same as 1/6 of a degree. And we downloaded, if you go back up to line 43, we downloaded data that were a resolution of 10 minutes. And a minute is 1/60th of a degree. So 10/60ths of a degree is 1/6 of a degree. Ultimately, it all makes sense that we would have data that have a resolution of 0.166 degrees, because that's the same as 10 minutes. Finally, we can look at the names of our raster layers. So each of these are T max and then a number indicating what month we're talking about. And then there's an explanation of that whole degrees, units thing in this big block of code that you can read at your leisure. So next I'm going to move forward to plotting. We can use base plotting functions in R, just as we did for the vector data set, to visualize our raster. So we can plot max temp historical. And what you should see is a series of 12 Earth-looking plots. I'm not sure why my plots are so small right now. Is that the case for everybody else too? Or
Yeah.
Yeah.
there's bigger? Okay.
Um,
When you plot a raster stack, which is a multi-layered raster, you will end up with a plot for each of those elements of the stack. So here we're looking at all of the months over the year and the maximum temperature of those months. If we want to just look at a single month, because 12 months of the year is hard to think about and probably not super useful for analysis, we can subset the raster. So first we can subset by layer, and we can do that in several ways. We can use the layer name or we can use layer indexing. And you can always use the question mark function if you're unsure about what something does. We can always look at the documentation. So we know we want to subset. We're not sure exactly what we need to do. Under usage, we see that subset for a raster involves this X argument and then a subset argument and then some other parameters. The X argument is our raster brick or stack, and the subset is either an integer or a character argument. So we can use the subset function with a character argument that is the name of the layer we want to use. If we're interested in working with January data, we can subset to use tmax1, which is the name of the January layer. And when we do that, we should have a single raster layer that has the same dimensions as the raster stack we used, but it's just one layer of that data set now. We can also use this other method with indexing, so that would be two square brackets at the end of whatever our stack is. And we can use either a number or the character vector corresponding to the name once again. So there's a few different ways to do that. Sample 2 and sample 3 are those two ways of using indexing. And then we can verify that we did the same function by using this all equal function with two different objects. And if it returns true, they are the same object. And as we see, everything worked out the same, so we can trust that any of those methods that we use for subsetting will work. So finally, let's return to that plot function, but just plot this single layer, which is the maximum temperature in January historically.
What do the colors signify?
Oh, great question. So the colors in any plotted raster represent the values in each of those cells. And here we're looking at a range in these spill values from about -400 to, I'm guessing that is positive. Yeah, it's probably positive 400. And the units in these world climb data sets are tenths of a degree Celsius. So if we want to provide some meaning to the values, we actually have to divide them by 10 to think about them, to conceptualize them. So what we're looking at, historical max January temperatures range from about -40 somewhere in the world to about +40 somewhere in the world. And if we look at the actual plotted data, this makes sense. A maximum January temperature in South Africa would probably be about 40 degrees Celsius. And a maximum January temperature in Siberia could ostensibly be -40 degrees. It's very cold there in January. Did that answer your question?
Yes.
Okay. To revisit plotting, we can also adjust the color ramp that we want to use. Once again, it's just using base plotting functions. So if you want to use what R calls topo colors, I don't really think they're very topographic, but we can use different color ramps if we want. And if we want to zoom in on an area without actually subsetting our data, we can define X and Y limits to the graphing space to just, for example, look at like North America. Everybody with me so far? Any questions up to this point? Okay. So we can also, rather than subset by layers, we can subset in space. If we're interested, for example, in just data about California, we could subset our raster to just include raster cells that exist within that California shapefile that we downloaded earlier. So let's return to our California shapefile. if you recall, it is in a Mercator projection, which is different from our long lat projection that the raster dataset exists in. Rasters tend to degrade when we change their conformation in space. So it's typically best, in my opinion, and maybe Ryan has an idea about this too, but I usually try to change the projection of my shapes rather than my rasters. So we have a Mercator projection of California, which we can use that proj4 string argument also to look at. But our max-jan histo raster is in long lat. So we need to do some rearranging in space and units to make these two match up. The RGDAO library conveniently has an SP transform function, which allows us to change the way shapes are defined in space to correspond with some other reference system. So we can use the SP transform function to transform the California shape to match the CRS of the raster dataset that we're working with. And so once we do that, we can add a little CA proj for string, and see that indeed now this new object is in the same reference system as our raster data set. So since we already have this North America subset of the raster data in the plotting window, we can add lines for our reprojected California shape. And we should see that it's really tiny on this screen, but that the California overlaps with actual California in the raster in a sensible way. So now that we have a polygon that we want to subset with, we can actually begin our subsetting. There are two functions that we'll use for this. There is crop and mask. When we crop a data set, we're basically constraining the data to the extent of our shape. So that's the x minimum, y minimum, x minimum, x maximum, y minimum, and y maximum bounding box of that shape. The thing about that is if you have a non-square shape, then you'll still have raster pixels that exist outside of the shape you're really interested in. So we also need to use the mask function, which will not constrain the final raster to the extent of the shapefile, but it will turn everything outside of that shape into NA cells. So if we take the product of our crop function and apply a mask to it, also using that California shapefile, we will end up with the data set that we're interested in. So we can compare them and look at the crop data set, and here you see that we're looking at a rectangular grid of cells, but that contains much more than just California. And then we can also run the mask. Oh, geez.
It's really tiny, but it's there.
Oh, okay.
I was trying to find it too.
Okay, it's there. I'm not sure why it's so. It shouldn't have that. It shouldn't have that extent. Oh, that's why. So this is actually a prime example of the issue that I was just trying to explain. The masked data set. All we did was mask the historical data set. What we really want to do is mask the crop data set. So if we convert line 134 to be a masking of what we had just cropped, then we should see a much better output, that is just California maximum historical January temperature. Everybody with me so far? Sorry for that little hiccup.
Can you just pause? You just changed.
I adjusted line 134 to mask the product of line 131. So we took this max Jan Cali crop and we're masking that rather than masking the full January data set. Questions? Okay. So we can sort of visualize that difference by using the extent function. And when we run extent on the crop, product. Oh, that was actually supposed to be wrong.
Yeah. I think it worked right. Yeah. You were good.
Wow, I got ahead of myself. Yeah, so I intended for that to be wrong, and you can tell because the next line of code is the right way to do it. Okay, so the extents for the crop and mask product on lines 142 and 143 should be different the way the code was originally written. And if we actually wanted to restrict our data to just California bounds, we would do what we changed the code to do, which is ultimately what we're looking at on line 149 and 151, where we are cropping the data and then also masking that data set. And when we plot that, it should look like what we had before. We can have the lines from our shapefile, and we see that they all line up appropriately. So now that we've managed to work our way down to a small, usable, functional, conceptualizable data set, we can perform some calculations on it. So as I mentioned before, the units from the world climb data are in tenths of a degree Celsius. There's some file size reasons for that. We don't need to get into it. But we can use some raster calculations to turn this into actual, like, real numbers that we can think about. So the calc function exists in the raster package and allows us to perform calculations on raster data sets. So for example, we can take our January historical temperatures and turn them into real units by basically taking whatever the value is, dividing it by 10. So when we run the Jan real units line, we'll end up with a map that has, or a raster data set that has units of degrees Celsius rather than units of tenths of a degree Celsius. So we can compare them and look at the historical data, which spans from negative 400 to positive 400, or we can use the real units data, and you'll see that the images look the same, but the values in those images have changed dramatically. So because the relative scale between the minimum and maximum value hasn't changed, there's not going to be an apparent difference in the pattern on the map. But the numbers that exist within that map are very different. And that's something that's super important to keep in mind as you're working with raster data sets. Finally, we can use a vectorized approach to change values in a single raster. So rather than using that calc function, you can say, divide the raster by 10. And that's what we're doing on line 172 here. Rather than plotting the maximum historical January temperature, we're plotting maximum historical January temperature divided by 10. And so this is a vectorized approach to do the same thing. And we see that the units are the same as the last time. The pattern is the same as the last time. Everything lines up, it's all the same data. The calc function, though, is also useful for working across raster data sets. So if we want to deal with several raster data sets at once, we're going to need to get some more data. So previously, we were working with maximum January temperatures. Let's download the minimum historical temperatures from the world climb data set on line 179 here, and subset those data to just look at January using that indexing method that we talked about before, and then plot it to see if it makes sense. Was everybody able to download the minimum temperatures? Anybody have any problems with that? Are we all at the plotting stage? Cool. So here we're looking at fairly similar spatial pattern in the data, fairly similar values, but you'll notice that they're not exactly the same because we're talking about minimum temperatures now. So the maximum value in this range only goes up to about 200, which is 20 degrees Celsius. But that would make sense in, say, Brazil or South Africa or Australia or whatever, because we're talking about minimum temperatures. So obviously, the minimum temperature wouldn't be 40 degrees Celsius. That's outrageous. So if we want to calculate across raster data sets, we need to stack them. So let's take our minimum and maximum January historical temperatures and stack them into a single raster data set that now has 2 layers. And we can get a rough estimate of the mean January temperature by calculating the mean value across those two data sets. So we'll use that calc function again. We'll take the historical January max and min temperature stacks and calculate the mean with that. I gotta warn you, some of these calc functions can take a really long time if you're using large rasters. So like if you download a whole MODIS tile or like several Landsat tiles or something, this can take a super long time on a computer. I'm sure there's you use the farm or just Python or something. It can take a really long time. There's also computing cluster functionality in raster package, so it's set up to be able to work with many computers at once. But yeah, so we can calculate the mean and plot it, and we'll see that once again, similar spatial pattern, but we would expect that because we're still just talking about January. And now rather than max or mins, we're talking about a rough estimate of the mean temperature. So at this point, we've generated a data set called mean Jan histo that is a mean January temperature historically on average from 1960 to 1990. What if we want to get an idea of how much temperature is going to change over the next several decades? Well, conveniently, also accompanying the world climate data that Robert Hyman's produced, he also has made available some of the forecasting data products. And so we can use the same get data function on line 203 now to get climate forecasts that are spatial. And so we'll use the CMIP5, which is like the Climate Model Intercomparison Project version 5. And we're going to get the maximum and then on line 209 minimum January temperature, well, full temperatures under the RCP 8.5 scenario, which is often referred to as the business as usual warming scenario. And we'll be getting those data for the year 2070. So we're comparing the future with historical. So let's access both of those two data sets as well. Notice that they're also a resolution of 10 minutes. So they will match up with the historical data that we're using already. And once you've downloaded them, we can look at them. If you want, you can run the CRS function, extent, and things like that to get an idea of what exactly the raster looks like. That also exists when you just print out the raster itself. And we see that the resolution, once again, is 0.166 degrees. Our reference system is in longitude and latitude. We have the same extent information. And because of that, we can pretty directly compare across these different data sets. So first, what we want to do is take a January subset from these forecast data sets. I'm going to use that indexing approach again. So we'll stack the maximum and minimum RCP 8.5 scenarios together just for January, again, using that indexing. And then we'll use the calc function again to find the mean January temperature forecasted for 2070 under the RCP 8.5 scenario. And now that we've generated this mean January temperature data set for the future, we can say, well, how different is the future going to be from history? And when you're dealing with just two data sets, you can also use an algebraic approach to do things like addition and subtraction. So let's subtract historical January temperatures from future January projected temperatures to create this diff product on line 227. And we can then plot that. What's really interesting here is that we don't see uniform expected warming. Remember that the units for the fill values represent tenths of a degree Celsius. So we're looking at a range here from 0 warming and also 0 cooling, because there's no negative values, it seems, up to, I'm going to guess, about 200, just trying to look at the scale and estimate, which is 20 degrees Celsius of warming. That might seem ridiculous, but the Arctic is warming much faster than the rest of the planet. And if we look at how the sort of spatial projections for warming are, we see that there's very little warming expected in Australia, Central Africa, South America. But as we approach the Arctic here, the Hudson Bay, northern Alaska, the Canadian high Arctic, there's a lot of those green values representing a much greater degree of warming. So I just answered the questions on line 232. You don't have to do any thinking. And then I think this is the second last thing I want to talk about. You can also extract values from a particular location using the raster package with this function called extract. The thing that's important to think about here is just like we needed the projection information for our California shape to match up with the projection information for the raster data set, if we want to extract data for a particular point in space, we also need those units to align appropriately. So let's say we want to get an idea of how much warming is expected in Sacramento over the next now 50 years compared to 1960 to 1990. We can look at this extract function, and it says that to run extract, you need to include an X and a Y. And the X is the raster data set that you'll be extracting from. The Y is the point or series of points that you want to do the extracting with. And they can be like spatial points and spatial polygons and other spatial type objects, or you can just generate your own matrix of coordinates, which is what we'll do. So we'll take the longitude and latitude of Sacramento, which I just Googled, and create a matrix where it's a one row and two column matrix where the left element is longitude and the right element is latitude, so that we have this single matrix with coordinates for where Sacramento lives on the planet. And then we can use the extract function from our difference raster to find out how much warming is predicted in Sacramento. So if we do that, we get an answer of 31.5. How much warming does that translate into Sacramento? Wow, yeah, 3.15 in Celsius. I was not the Fahrenheit. That was a leap. But so that is under a high emissions RCP 8.5 scenario. If we did the same thing with emissions reduction scenario, like the RCP 4.5, we probably wouldn't see a number quite so big. So now the last thing that I want to talk about before I just turn you loose, I didn't realize how long this was going to take, sorry, is the cell stats function. So we can get an idea of what's going on across a full raster data set pretty quickly. So we can use different functions such as mean or standard deviation to get a broad scale idea of what's going on at the aggregate level of the raster. So if we want to get, for example, a mean global temperature in January, we could run this mean statistic on the main January historical data set with cell stats. And we'll see that the average January temperature across the planet is negative 18.68 tenths of a degree Celsius, which is negative 1.8 degrees Celsius. We can also use cell stats for raster bricks. And when you do that, it'll return a series of values, one for each layer of the brick or the stack. So if we recrop and mask the maximum temperature historically, we can run cell stats on that, and we will see that it returns 12 values, one value for each layer of the stack. And then we can plot it to look over the course of the year. Historically in California, the average temperature spans from, what is that, like 1.4 degrees, 14 degrees Celsius up to, man, I wish there were more units on this, up to about 30 degrees Celsius. Does that make sense conceptually? Like when you think about California temperatures? Cool. So at the end, I have a little challenge where I'm asking you to compare the predicted temperature in a month of your choice between two different climate warming scenarios, the RCP 4.5, which is an emissions reduction scenario, and the RCP 8.5, which is what a lot of people call the business as usual scenario. And I want to ask you, how does carbon mitigation affect the expected warming? And does it affect that anticipated warming uniformly? So I would recommend first just writing out some pseudocode, thinking about the problem that you're tasked with. You're probably going to have to download some additional data using that get data function, and think about how you want to stack things, how you want to use the calc function, raster stats, cell stats and stuff, cell stats and things like that. But with that, I don't really have anything else to say. So if you guys have any questions, I'm happy to take them. If you want to work on the challenge, you can. If you want to do homework, you can do that too. Yeah.
I got a question about mask. To understand actually crops the data set you're working with. Can you just say again, I saw what mask did, but what's going on behind the
Sure.
data set?
Yeah, so with mask, you have some sort of shape. And if you just put that shape over the raster and then erased everything outside of it, that's essentially what mask is doing. It's converting all the cells that are outside of the shape into NA values, which are like not numbers. But there's also an option in the arguments. If you look at the documentation, there's, I think it's called invert or something like that, where you can mask everything inside the shape. So if you have like an image of the Owens Valley and you don't want to include the Owens Lake, which is like a dry bed in the south, you could draw a polygon around that and mask the inverted lake, and it would just remove everything in that area.
So crop keeps the data set rectangular, and the data set stays rectangular. Mask just puts NAs in there, it's not taking time or running calculations on these things, it's also not plotting.
It's also, yeah, I find it super useful for like trying to like grab an audience's attention, because if you have a bunch of stuff outside your polygon, people start looking at that and it's not what you're interested in. So like the base image on the head of my slide here, that is a masked data set that's just Mariposa County. And so you don't see anything outside of the county. It's just masked to just be that. Anybody else? Cool. Well, thanks for coming, guys.
Thank you.